Jai Hind everyone. I am Shruti Jain, Assistant Professor, MCA Department from Garg Engineering College, Ghaziabad. The subject on which I am going to talk about is the operating system. That the subject code is KCA203 and the topic is the CPU scheduling. The target students here are the MCA second semester first year students. So, coming to what a CPU scheduling is basically. So, whenever we talk about the multi-programming concept, it has that the concept talks about multiple processes that are running at all times in the CPU for a maximum CPU utilization. So, if we are talking about a simple computer system, the CPU where only one process is running at a time. So, in that case the CPU would sit idle and all this waiting time is wasted for the processes that are entering one after the another into the system. So, this problem is being taken care of by the multi-programming where we try to use this time productively and the several processes are kept into the memory at one time. So, when one process has to wait, the operating system takes the CPU away from that process and gives the CPU the another process, and this kind of pattern continues. So, when we are talking about scheduling, it is a function of the operating system where almost all the computer resources are scheduled before the use. So, starting with the CPU scheduler, whenever a CPU becomes idle, the operating system must select one of the process in the ready queue that is to be executed. Now, how this selection process happens? It is the selection process is carried out by the short term scheduler. What does the scheduler does? The scheduler selects from among all the processes that are available in the memory that are ready to execute and take one of them and allocate the CPU to them. Now, when we are talking about ready queue, it is not necessarily a first in first out as a term queue talks about. It could be that all the processes are there in the ready queue and whatever process gets the resources, that process enters into the execution. So, why are we talking about what are the different criteria for scheduling? The first one is CPU utilization. So, we want the CPU to be utilized to the maximum. So, but maximum utilization is basically not possible. So, it usually range from 40% to 90%, where when the CPU usage is 40%, we say that the CPU is lightly loaded, and when it is 90%, we say that the CPU is heavily loaded. Throughput is the number of processes that are completed per unit time, that may range from 10 per second to 1 per hour. Turnaround time is the time required for a particular process to complete from starting from the submission time to the completion time, the time when the process enters into the system and get executed. Waiting time, how much time the processors spend in the ready queue waiting their turn to get on the CPU is the waiting time. The next one is the response time. The response time is the time taken in an interactive program for the issuance of a command to the commencement of the response. When the command is issued and it is being executed, that is the response time. So, in general, whenever we talk about the CPU utilization, one wants to optimize the average value of criteria, that is maximum CPU utilization and throughput, and minimize all other. So, we have different scheduling algorithms that we are going to talk about. They talk about how the processes are entering into the system or are getting executed. So, the first scheduling algorithm that we are starting with is the FCFS, that is first come first serve, which is like a queue. When a process enters, the process is executed in the same pattern it is getting into the system. So, here if we look over here, we have the process P1, P2 and P3 that are entering into the system for executing. The burst time, that is the execution time of P1 is 24, the execution time for P2 is 3 and the execution time for P3 is 3. So, if we look for the waiting time that we have for all the processes, so here the waiting time for process P1, since the process P1 enters as soon as it enters into the system, it does not have to wait. So, the waiting time for P1 is just 0 milliseconds. But if we look here for process P2, which takes only 3 milliseconds of execution time, has to wait for 24 milliseconds because the process P1 is executing. So the waiting time for the process P2 is 24. Similarly, because process P2 took 3 milliseconds to execute, the burst time for P1 was 24. So the total waiting time for process P2 was 24. P2 executed in 3 milliseconds. That is the burst time for process P2 is 3 milliseconds. So this process P3 for process P3 the waiting time becomes 27. So in that case, if we identify the average waiting time, we'll add up all the waiting times. For P1 it is 0, for P2 it is 24, and for P3 it is 27. We divide it by 3 because we have 3 processes over here. We get the average waiting time of all the 3 processes as 17. But in case the pattern in which the processes were entering was changed, and we in the initial stage we had the process P2 entering, P3 entering, and at the last the longest process, that is P1, enters. In that case, the average waiting time decreases because P2 does not have to wait, so its waiting time is 0. P3 waits only for 3 milliseconds and P1 has to wait for 6 milliseconds and it has to execute. So in that case, the average waiting time is just 3 milliseconds, which is much better than the previous case. So it all depends upon the type of processes that are coming into the system. If a very long process is entering, the average waiting time would be more in the FCFS case, and if the process is entering, the process that is entering is of very small burst time, the average waiting time would be less. The next scheduling algorithm that we have is shortest job first scheduling, where it is being considered when all the processes enter, the process which has the smallest execution time is executed first. So if we look over here, in the table we have the process P4 that takes the least, that has a smallest burst time, or that takes the least time for execution. In that case, P4 is executed first, where the waiting time for P4 is just 0 milliseconds. The next one is P1, which is to be executed because it is a next higher process which has the less burst time. So its waiting time is just 3. For P3, we have 7. The P3 will be executed with a waiting time of 9, and at the last we have the P2 that is being executed with a waiting time of 16. Now when we are going to calculate the average waiting time, what are we going to do? We are just going to add all of them, 0 plus 3 plus 9 plus 16, and we are going to divide it by 4, for which we get the average waiting time as 10.25 milliseconds. Now, this shortest job first can be proven to be the fastest scheduling algorithm, but the major problem that occurs is how do we know how long the next CPU burst is going to be, because it is not necessary that all the processes are going to enter at the same time. So there it faces a particular drawback. Otherwise, if we talk about the shortest job first scheduling, it is much better as compared to the first come first serve. The next algorithm that we have is shortest remaining time first algorithm. Now, shortest remaining time first algorithm, what does it do? It identifies how much time is remaining for the execution to be done. So, for example, here we have the processes that are coming with different arrival times. Here the arrival times are different. So, process P1 entered first, and since there was no process at that time, so the process P1 was allocated with the CPU. Now, how does it work? When the process P1 entered, since there was no other process which entered, the process P1 got the CPU and it started executing. But the algorithm that we are talking about is the shortest remaining time. So, as soon as the process P2 entered at the next millisecond, it had the less burst time as compared to P1. Now, when it had the less burst time as compared to P1, what will happen? This P1 will be preempted and P2 will get the CPU. Now, this preemption means when we are talking about the shortest remaining time first algorithm, here it is a preemptive algorithm, because when the jobs get preemptive according to their remaining burst time. So, when we are talking about SJF, it can either be preemptive or non-preemptive. The preemption occurs when any new process arrives in the ready queue that has a predicted burst time shorter than the time remaining in the process. Now, whose burst time is currently going on in the CPU. So, preemptive SJF is sometimes referred to as shortest remaining time first scheduling that we are studying right now. So, when this P2 came up, the P2 was executing and in the next millisecond, the process P3 came. But this process P3 had the burst time of 9 milliseconds, which was larger than the P2, and hence the P2 will execute the way it was doing for the next millisecond. Now the process P4 came. Now this process P4 was arriving at 3 milliseconds time. It also had a burst time that was more than this process P2, due to which the process P2 will execute completely. Now, when this process P2 executed completely, this process P2 was done. Now we are left with process P1, whose burst time is now left with 7, because for 1 millisecond it has already executed over here. Process P3 has a burst time of 9 milliseconds and process P4 has a burst time of 5 milliseconds. That means the shortest remaining time over here is the process P4. That is why the process P4 enters into the system with a waiting time of 5 milliseconds and it will execute because no other process is entering into the system, and all those processes that are already there in the system are have bigger burst time as compared to this P4. Now P4 executed fully with 5 milliseconds of burst time, and here process P2 had 4 milliseconds of burst time. When P4 executed, this also is done. Now we are left with P1 and P3. P1 has a burst time of 7 milliseconds and P3 has a burst time of 9 milliseconds. Accordingly, we have P1 which has a less burst time. Therefore, P1 will be executed for 7 milliseconds because 1 millisecond was already taken up by when it was executing at first. When this 7 was executed, we are left with P3. P3 will be executing. Now, how are we going to calculate the waiting time? The waiting time for, if we look at the table for P1, P2, P3 and P4. If we look for P2, P2 came at 1 millisecond. The process P2 came at 1 millisecond, and at the same time, the time when it entered into the system, it got the CPU allocation. Therefore, the waiting time for P2 is 0, because as soon as it entered into the system, the job came into the system, it was allocated with the CPU, and hence the waiting time for P2 is 0. Now, if we talk about the waiting time for P3, the process P3 has a waiting time of 17 over here, but it came 2 milliseconds late, and hence the waiting time for P3 is 17 minus 2, that is 15. Now, talking about the process P4, the P4 executed here after 5 milliseconds. That means the P4 process has to wait for 5 milliseconds, but because it came into the system 3 milliseconds later, therefore the waiting time for the process P4 is 5 minus 3, that is 2. So if we look over here, this one is for P4, this one is for P3 and for P1 it is 10 minus 1. Why? Because if we look here, the waiting time for process P1 is 10 milliseconds, but it already executed for 1 millisecond over here. That means when the process entered into the system, it got the CPU and it executed for 1 millisecond. Therefore, we'll subtract this 1 millisecond from the total waiting time for P1. Therefore, the P1 has to wait for 10 milliseconds minus 1. This one is where it has already executed when it entered into the system. So, this is for P1. So now when we are going to calculate the average waiting time, we'll add up all of them, 9 plus 0 plus 15 plus 2, and then we'll divide it by 4 in order to get 6.5 milliseconds as the average waiting time. If we are going to calculate it on the basis of shortest job first, that is non-preemptive, the algorithm that we had just discussed over here, in that case we'll find out that the non-preemptive SJA will give us the average waiting time as 7.75, and 8.75 will be for if we consider the algorithm as first come first serve. Now, drawbacks of shortest job first, we can have the problem of starvation, where the constant arrival of the jobs that are short and have less burst time can keep longer ones from running, and there is no way, and the other one is there is no way to know that the completion time of the job is how much. So, starvation is basically a situation when a process has to wait for a very long time in order to get the resources. It could be a possibility that a higher priority process came up, or a process of the short jobs with less burst time has came, due to which the longer processes or the lower priority process has to be into the system for a very long time and they do not get the resources. So, that problem may occur when we are working with shortest job first. The next type of algorithm that we are going to talk about is the priority scheduling, where the priorities are assigned to the processes that are entering into the system. We normally give lower value to a higher priority process and higher value to a lower priority process. So, if we look over here, we have all the processes that entered into the system. Now, the process P2 has a very less value, that is the that is the highest priority. So, this P2 will be executed first as soon as it enters into the system and will take the burst time of 1 millisecond and will execute. The next higher value is for P5. So, P5 will execute and will continue to execute till it completes its execution. Then the process P1 will execute, followed by P3 and P4. So, this is how we will get a Gantt chart. Calculating the average waiting time will identify that this is based on the priorities, where the process is entered with some priority and it get executed. But now again we have a problem of starvation, because it might be a possibility that every time a process is running, a higher priority process comes up, and that the already running process is not able to continue or complete itself because a higher priority process has come up and there is a preemption of the processes. So, in that case we can suffer with the problem of indefinite blocking or the starvation problem. For that, what we have a solution? We have a solution of aging, where we increase the priority of the processes on the basis of the time they are waiting into the system. If they are waiting for a very longer time, we increase their priority so that at certain point of time they become a high priority process and get executed and moves out of the system. The next scheduling algorithm that we have is round robin scheduling algorithm, where what happens is we divide the time interval into time quantums, and a particular process that is coming into the system is given that particular time quantum to execute. If the process completes its execution within that time quantum, then the process will be executed, will be considered as executed. In case the process is not able to execute in that time quantum, then the other process will come up and it will be preempted by that process. So, that here the swapping in and swapping out comes up, where the process is swapped out, the process once the time quantum gets completed, the process swaps out and the other process enters. So, if we look over here, we have a time quantum of 4 milliseconds. Now, the process P1 comes up because the burst time of P1 is more as compared to 4 milliseconds. So, it executed for first 4 milliseconds over here, sorry, for 5 milliseconds it executed, and then it was swapped out of the system and the process P2 came up with 3 milliseconds. Because the burst time was less than the time quantum, the P2 was allocated the system and it executed in 3 milliseconds. After that, P3 came up into the system and it also executed because the time quantum, the value of time quantum was larger than the burst time. After that, the CPU was allocated to P1 and it always executed after every 4 milliseconds and it executed. And later at 30th millisecond, it was complete. So, how do we calculate the waiting time for the processes? For process P2 is simple, it is 4 milliseconds. For process P3, it is 7 milliseconds. Now, if we are going to calculate the average waiting time for P1, the waiting time when P1 entered into the system for the second time was 10 milliseconds. After that, it was continuously executing. But for the first 4 milliseconds, it was already executing over here. So, the waiting time for the process P1 is 10 minus 4, that is 6. So, waiting time for P1 is this much, for P2 is 4 and for P3 is 7. Once you add up all of them divided by 3, you will get the average waiting time. Now, the performance of our round robin is sensitive to time quantum selected. If the time quantum is large enough, then the round robin reduces to first come first serve, because every time the process enters, the time quantum is larger enough for it to execute, it becomes a first come first serve criteria. If it is very small, then each process gets 1 by nth of the processor time and share the CPU equally. So, if we talk about the round robin, in the round robin scheduling, it is similar to first come first serve, except that the CPU bursts are assigned with limits that are the time quantum. When a process is given the CPU, a timer is set for whatever value has been set for time quantum. A ready queue is maintained as a circular queue. So, when all the processes have had a turn, then the scheduler gives the first process another turn and so on. As we have seen in this example where we have process P1, P2, P3. Once the process P3 executed, then the turn again was given to the process P1. So, how do we evaluate these algorithms? The evaluation of these algorithms depends upon the criteria on which we are executing the processes. The one criteria could be maximize the CPU utilization if the maximum response time, when the maximum response time is 1 second. So, once the criteria on which you are evaluating the algorithm is decided, only then we can decide which algorithm is best suitable for a particular process. So, we have the modeling that we are using when we are evaluating an algorithm is deterministic modeling, where if a specific workload is known, then the exact values for major criteria can be easily calculated and the best determined model or the algorithm can be taken up. For example, if we consider that the workload with all the processes arriving at a time 0 and the resulting schedules determined by 3 different algorithms. So, in case we have these 5 processes that are there into the system, and we are trying to identify which among these 3 are the best one. So, we will try to calculate the average waiting time in all the 3 cases. So, the first come first serve, or the first job will be taken up, executed, then second, then third and fourth. Non-preemptive shortest job, first the shortest job will be taken up, that is P3, followed by P4, P1, P5 and P2. If we talk about round robin, we have a time quantum of 10 milliseconds. So, in that case, the first one will be executed followed by P2, but because P2 is a longer job, it will move on to P3, P4, P5. Now, P5 also needs one more time. So, P2 and P5 will swap and will execute. So, later on when we calculate the average waiting time for FCFS, we identify that it is 28 milliseconds. For shortest job first, it is 13 milliseconds and for round robin, it is 23 milliseconds respectively. So, this deterministic modeling is fast and easy, but we should know what process is coming with what burst time, and that is the input should be known to us and the result only apply for that particular set of inputs. So, however, by examining multiple similar cases, we can determine certain trends and we can identify without actually calculating which algorithm is best for what set of processes that are coming into the system. That's all.